Thank you, Gareth, for the introduction and for the invitation. So for me, it's really a pleasure to show you some live script that I have been doing the last weeks for this meeting. So basically, we will be talking about how to animate things in MATLAB. And you would say, okay, why I need to animate things? So the answer is really simple. Just because you want to show something to your peers, or just because you want to get to know what's the real reason of a certain very complex movement. So in this talk, we will go from very simple line animation to very complex and multi-agent systems animation. So first of all, we will start, for example, with time histories. In this line of code, what I've done is just to define the simulation time, and then to define, for example, a system, which is a low pass plus 2 elastic modes. So basically here we are defining the frequency of the low pass and the damping, and here the frequency of the first elastic mode and the frequency of the second elastic mode. So here we define the system, and here we simulate the step response, right? So then we have 2 ways of animating things. One way is called the hard way, or because we will be using a lot of overhead for MATLAB for plotting this figure. So for example, let's start plotting the figure. So using the hold on and hold off button, what we are going to do is just to first initialize the figure, then plot the first line, then hold on, plot another line, and then in the next loop, we completely delete the plot and plot it once again. So as you will see, this will generate some fancy animation of the time response. So I call it the hard way because MATLAB is basically plotting and deleting the plot, plotting and deleting the plot. So this takes a lot of time. So you can do it here more easily using some fancy properties of the plot function, which is the X data source and the Y data source, and also the Z data source. And with these properties, you are telling MATLAB which is the source of the information of the plot it must represent in this figure. So basically, here we only need to plot once, and then during the loop, we just need to update the sources of the X data and Y data of each one of these plots. So these lines, with these lines, we get the same results, but using so much less computations and time. So fair enough, this is an example of animation of figures and simple lines and this kind of stuff. So
sorry, Rodney, quick question. So this is super cool. So there's a question that came through is, I noticed that you're doing these animations in the figure. How do you do those animations inside the live script itself?
Because if I do it in the live script itself, it does not pop up nothing because, for example, if I run this cell, it seems to get busy plotting the figure somewhere, and when it ends the live script, then pop-ups here the figure. Have you seen? And no figure pop up. So I need to for this one, I don't know why, I need to evaluate them with the F9 button. I don't know why.
Very good. So I think there's some of in the newer versions, there's animation capabilities built into the live script, and there's a few more lines of code needed to make that happen. But I think most people come from the traditional .m files, and indeed that's what you see. Yeah, very good.
Okay. So going forward with more complex 3D objects. For in the MATLAB file exchange, there's a very useful free toolbox which is called STL Tools, which allows you to load into MATLAB some very complex 3D forms with the STL extension. So here I'm adding the path to the toolbox, and then I'm adding the path where I have stored some fancy B2 Spirit 3D model. So using just one line of code, I get all the vertices and faces of this STL file, and then also with just one line of code, I can plot the 3D object using the MATLAB patch function. So if I evaluate this cell, what I get is this fancy figure of the 3D model. So as you have seen, it's very simple and in one line of code. So up to this point, we have only learned how to animate a line and how to load a 3D model, but not how to animate this model, which is the big deal here.
So maybe just one more question, Rodney. So before you keep going into the airplane, so this is super cool, the STL. Gerard asked the question of animating the line. He uses the command comment in MATLAB. Is there an added value why you didn't show the comment function here? Or is this just to show that this is the traditional trajectory that most people starting with animations and live scripts go through?
I don't get the point with comment.
Comment. There's a function in MATLAB.
Comment.
Where it leaves a trail when you do an animation. And I think the amount of control you have is maybe limited, but it does give an animation.
Well, I was not really aware of this function. If it exists, it's for sure it will be much easier than this one.
So
but for example, this one, what you really get with this one is the ability to then export this animation to a GIF file or to a movie file. I don't know if the comment function also have these capabilities.
That's a good point. I think it's a little bit more cumbersome. Here you have much more control over it.
Yeah, basically I like a lot to animate time histories and save it as GIF images, just for entertainment purposes on LinkedIn and whatever. And this is the way I do it. But I will take a look to the comment function. Thanks for the suggestion. So going forward with what MATLAB has to offer us to animate 3D objects and to animate lines and whatever, MATLAB has two very important and very useful functions, which is the HG transform and the make HG transform. So basically, the HG transform is a function that allows you to collect a lot of 3D objects and make a unique set with these objects and apply at once to all of them certain spatial transformation. So for example, here I have included some example from MATLAB documentation, and basically it's how to animate different surfaces. For here we set the figure, we initialize the group handle, okay? So now we get this cylinder, and with this cylinder coordinates, we plot one surface here, another surface here, and 6 different surfaces here. So if we had not this HG transform function, we would need to transform each one of them in each time step. So the fanciest thing here is that we assign to the H handle the parent, which is T, and T is a transformation group. So when we evaluate this animation, we only need to say, okay, let's set this transformation matrix to the transformation group T. So basically here we are saying, okay, I want to rotate around the Z axis, R degrees, and I want to scale this transformation group by a factor of R divided by 4, and then make the transformation. So basically, if I animate this one, okay, this one is one of those which does not pop up. So I need to. So as you can see, each time we set, okay, the transformation matrix of this transformation group is this one, all of the children get the same transformation. So in one line here, we rotate and scale the 6 different surfaces. So this is the magic of the HG transform and the make HGT form. So with this very simple example, you might not be aware of the real potential of this function. So here I have put as a more complex example, which is an aircraft which has 2 ailerons, okay, 2 elevators and 1 rudder, and as many aircraft within each aileron and within each rudder and within each elevator, they have what we call a twin tap. A twin tap is a very small surface which is deflected up and down, so as the pilot can trim the flight control stick. So using 0 forces in the flight control stick, the flight control surface stays in a certain deflection. So the question is here is how to move this little one surface, which moves around this aileron surface and which is moving with the aircraft, which is also moving. So this it starts to get real real complex. So with this solution, with the HG transform, what we can do is the following. So basically, what we will do is to assign the aileron trim to an HG transform. Then this one we will assign to a parent, which is the whole aileron surface, and the whole aileron surface will be the children of the aircraft. So basically, we have an HG transform, which is the rigid body of the aircraft, then an HG transform, which is the aileron plus the aileron trim, and then a single HG transform, which is the aileron trim. So in this way, if we move the rigid body of the aircraft, all the children move. But if we only move the aileron, the rigid body does not move, but the aileron move and the aileron trim also move. So this is somehow the potential of these functions. So
maybe, Ronnie, just a quick thing. So I think circling back to the first initial questions, right? So you presented a very simple example of animating a line, and then some of the MATLAB users are like, well, you could use Comet, or you could use the animated line in the live script to get that going. But I think what you're showing is a very interesting way of doing 3D graphical representations inside MATLAB, and that is the added value of your approach versus the animated line and the Comet, because what you're doing here is you're a few steps ahead of everyone, and I think this is a very cool example. So but you need to understand the parent hierarchy, which I think follows most of the graphical languages constructs, right? So this is not an abstract thing, it is common across other languages. So and Ronald, he made a comment of saying this looks just like OpenGL, and I believe underneath the hood this is OpenGL rendering capabilities kicking in here. So thank you very much, very cool. So that's just to solidify the earlier questions.
So basically here I have downloaded already a 3D model of a Saab Gripen aircraft, which has several primary flight control surfaces. They have 2 flaperons, they have 2 canards, 1 rudder, and 2 air brakes, and 2 leading edge flight control surfaces. So I have already split this 3D model in these STL files. So what we are going to do here is try to animate the movement of the left canard surface. So basically, here in this script, what we are doing is to define the STL files, which will be part of the rigid body, then define the colors of each one of these STL files, then define the transparency factors, okay, and also define an offset factor just to center the 3D model in the center of the axis, and then going through all of these parts just to call the STL read function to read the STL file, and then we will do the same with the flight control surface that we want to move, which is the left foreplane. So I will and then we will go for plotting the figures. Okay, so I'm going to plot. Okay, so here we have the 3D model, and here we have the flight control surface that we want to move, right? So in order to move these flight control surfaces, what we need to do is to define the reference point or the rotation point, and to define the rotation axis. So basically, we will use this pickup function. So we will pick this point. We note the 3D coordinates, and then after that, we need to define the rotation axis, which in this case will be some line parallel to this direction I'm sending. Okay, so I have already made these steps. So I have picked up the rotation point coordinates, and I have written the rotation vector. So now I'm going to plot this one also on top, just to double check. So basically, our flight control surface will be rotating around this point, and a positive rotation will be in this way. Positive rotation in this way. So basically, what we need to do is just to animate the things. So we start a new figure. We start the transformation groups, which is one for the aircraft body, and the other one, which is for the flight control surfaces. And here is the trick. The parent of this flight control surface will be the rigid body, just like as the previous example. Then we define the rotation angle for the flight control surface, and let's define that the aircraft is rolling again, around the rolling axis with this time history. So first we plot the aircraft, which is here. Then we plot the flight control surface, which is here. Then we set the axis properties, and everything is ready. And here is where we perform the animations. So basically here we are saying, in each time step, I want to rotate around the x-axis a roll angle, okay? And this rotation matrix is being applied to the rigid body transformation group. So during this rotation, the flight control surface should be moving also with the aircraft. And then here, what we are going to do is just to translate or transport the flight control surface to the 000 origin, then rotate around the rotation axis, and then get back this flight control surface to its original position. And then here we are setting the transformation group for the flight control surface will have this transformation matrix. So if I've done things good, here you will see as the aircraft rotates, also the flight control surface rotates while it's turning around the rotation point that we have selected. So this is an example. So doing the same thing for all the flight control surfaces, I have done the work here, and just to save all the information here into a MATLAB file, or into a mat file. So basically, all the information here is gathered, and now here we are checking that we have made all things good. So here we have the whole aircraft, and on top of it, we have defined all the rotation vectors and the rotation points. So we are checking that we have not made any mistake. So everything is rotating around the good axis, and we have the 3D model ready. So now we will be moving to the animation function, which is the one which will output something fancy like this animation. So basically here we are saying as input, which is the MATLAB file containing all the information of the 3D model, and then the Euler angles, heading, pitch, and bank of the aircraft. Then the roll and pitch command of the pilot to plot it here in a cross plot. And also some information regarding the angle of attack and angle of side slip, which are aerodynamic parameters, which is basically to plot this blue line here, which is telling you in which direction the speed vector or the aerodynamic speed vector of the aircraft is pointing to. And then the flight control surfaces deflection, sorry. So basically we start loading the model, which we already saved. Then if we want to save the video, we start the video object. Then we get the dimension of the model and initialize the figure. And here comes the initialization of the transformation groups, which is basically one for the rigid aircraft and then one for each one of the flight control surfaces, which is parent is the aircraft. And these transformation groups goes for these rolling, these circles, which tells you and give you more inside information about the actual angles of the aircraft. So basically here we plot the objects, the aircraft, we plot flight control surfaces, we define the axis, and then here we start to plot all these lines. And then we get some text. So as we can see in the animation, which are the actual values of, for example, the load factor, the Mach number, the altitude, angles, and whatever, and the time of the simulation. And finally, we perform the animation loop, which is basically a little bit more complex than the previous example, but the same way. We compute the transformation matrix for the pitch disk, for the roll disk, for the roll line, for the pitch line, the heading line, and then for the aircraft body, which is basically rotations of Euler angles, heading, pitch, and bank, and the rotation of the flight control surfaces. Then we perform some updates of the aerodynamic speed vector, and also we compute the updates of the text handles. And at the end, we change in order to give us more information, in which we call what we call a departure from control flight, is when the aircraft start to move in a region of the flight envelope which is not safe. So for example, here I have changed the aircraft color from gray to red if we exceed certain parameters, load factors or angle of side slip or angle of attack or whatever. And that's all. So going to a real example, which is the fancy part here. So I have used this open source simulator, which is called the Admire, which is an open source, let's call it this way, low fidelity model of the Saab 39 Gripen, which is basically the aircraft we are plotting in the 3D model. So here I have, I just need to load some the simulation results, which are scissor maneuver. And here we are just putting the heading, the pitch, the bank and roll, and finally calling the 3D animation function. So if I play this one, what you see is all in action.
So this is super impressive. It's wonderful to see. So I'm sure many of us have got tears of joy as we're looking at this. You might not be realizing it, but I'll tell you that up front. But there were a couple of questions that came through while we were showing that animation. Is 3 of them, I think. Ronald asked, are you using any of the MathWorks toolboxes, and I think you mentioned you're using an open source toolbox. So I think if you could speak a little bit about what toolboxes from the MathWorks and or community are using, that would be nice. And then two other questions were, did you investigate using, I think it is called the Simulink 3D animation to do this inside Simulink? Mm-hmm. And another person asked, well, what about the Simscape multi-body tools from the MathWorks? Did you look at that to do this? Maybe you could share a few words on that.
Yeah, going to the first question, I think this is plain MATLAB, no toolboxes required, because the only more complex function is the HG transform, and HG, these functions are from plain MATLAB. So there are no special toolboxes. And the other question, Gareth, can you repeat? Was related to the Simulink environment?
Well, so I think you said you're using the STL community toolbox.
Oh yeah. This is open source. This is you can find it in the file exchange.
And yeah, what was it called again? Sorry.
Is STL tool.
Okay, STL tools. Okay, very good. We'll put that in the chat. Then the other question was, did you look at some of the other Simulink toolboxes? And the 2 of them that appeared are the Simulink 3D animation and the Simscape and Simscape multi-body. Did you investigate any of them for these kind of simulations? In particular, because you have a Simulink model.
Yeah. For sure, I took a look, but what I did not like at all of this representation is that they came with a lot of overhead of representation of the environment, the 3D textures, a lot of things that in our day by day we don't. This is just an engineering tool. It's just to see a very complex maneuver, to really get to know what's going on, and not looking into the time histories alone, because sometimes you look into the time histories and you don't really get the source of the error or the source of the complication that's going on in this maneuver. So, for example, in this maneuver, which is a departure from control flight, if you look at the time histories, it might be difficult for a non-expert eye to see what's going on. But then if you play this one, you start to see that, for example, here the flaperon gets saturated, the rudder gets saturated, and then here you start to get a lot of side slip angle because of the rudder being saturated, and then you depart completely from control flight. So going back to the question, yes, but this tool gives you a lot of flexibility that I have not found with the Simulink visual environment.
No, fair enough. Very good. So I think that's a good answer, and I think it's clear you've invested some time in making this, and I like the animations. So no, very good. Please continue.
And then just some example for the maneuver. Just So as you can see, this is very visual. So this is for single agents or single 3D objects animation. So we are going to a little bit more, add more agents for more 3D forms in the animations. So we are going for the multi-agent 3D animation, which is something which I found it very useful because I have been playing around with a simulator that I built up on my own here at home, just to play with some automatic air-to-air refueling simulations and to play around with different flight control logics and to different collision avoidance flight controls algorithm, just to play around with them and see which is the output of the simulator. So this 3D animation gets me a lot of information. So as you can see here, so we will go in to see some examples. So basically, I have built up some very simple simulator here in MATLAB, which is basically a multi-agent simulator, and it's only for aircraft, and it's very simplified because what I'm assuming here is that the autopilots of the aircraft can be modeled as a first-order dynamic model, which is fair enough. So basically, I have modeled it in MATLAB because it gives me a lot of flexibility of changing the number of agents and performing different simulation by just changing this number. So the real deal here is the visualize function. So basically, in the visualize function, we are using the same tricks that I have shown you in the previous slides or in the previous scripts. And basically, what we are doing is to apply the same thing, but to different agents. So basically, in this function, which is already prepared to be used as a MATLAB function in Simulink using this coder extrinsic. So you can also visualize the output of simulations in Simulink in real time. So basically, what we are doing here is just to initialize the figure, then read the tanker aircraft, which is an A330, using the same function, strread. Then we perform some rotations to orient it in the way we want, and then plot it, the tanker, and then plot the simulation time. And then we are going for the agents or the assets, which will be a Eurofighter Typhoons, which here we read the 3D models and we perform the plotting of end planes using the same function, using the HG transform and make transformation matrix, which uses within the same algorithm to compute the rotation matrix. Then we plot each one of the agents, and then we plot some trajectories and some additional information. So going on to the output of the simulation, here we will be simulating the automatic air-to-air refueling of 5 different aircraft, which are being controlled by the autopilot automatically in turbulent conditions. So I will play the simulation. So here, what you see is in a white square is the target position of each aircraft. And as you can see, each aircraft is maneuvered so as to get to that position. Also here, after getting to this long position, here in red, what you see is the command from the auto throttle. And then, oh, sorry. I'm trying to zoom the figure. So, okay, in magenta, what you see is basically the command from the heading autopilot. And in red, what you see is the command from the throttle autopilot, which is slowing down the aircraft up to getting to the position. Then once they get to the position, this one start to go to the what we call astern position, which is a little bit behind the hose. Here I have not plotted the hose, but here's a hose and drag. And then this one goes to this position. Let me rotate the figure so as you can see it better. It's a little bit complicated to. Okay, and then going here. Now you have a clearer view. So this one is performing the refueling. Here is the command from the autopilot, which is as we have turbulence here, as you can see, the aircraft are not staying at their position at the best, but the autopilot is doing the best. This one has already completed the refueling, so it's moving back to the safe zone. And then when this agent gets to the safe zone and goes to the after refueling position, which is in this side of the tanker, then this one should move to what we call astern position. So as you can see, this type of visualization gets you a lot of information of what's going on and if you are doing the things right or not. So this is with 5 aircraft. So as I have told you before, why modeling this in MATLAB is because it gets you a lot of flexibility, because now we are going to get the party started and simulate 15 flying objects. So here we will start.
An interesting question while you're doing that is someone asking the question is there any limitations in terms of computation? So this approach?
No, it's in terms of flexibility, because from as far as I know, you will need to put 15 different blocks if you want to play with 15 aircraft. And then if you want to play with only 2, you need to delete them, save the model, then play again, make that everything within is really get well connected. And in MATLAB, it's just a few lines of codes. So as you can see here, the collision avoidance start to play around, because this aircraft wants to get there and the other one tries to get there. They are not colliding. It's just a feeling of death.
This is very impressive, and it's reassuring that these simulations do take place, Rodney. I feel much safer now when next time I fly and I go over Schiphol.
This is just some own work, or when I get bored at home and say, okay, I want to play around with different flight control characteristics and flight control laws for distributed agents. So here's a perfect simulation environment to get the things done and to play around with different architectures, and for sure this type of visualization gets you a lot of information. We will see when they all get to the position, they start to move to the left hand of the tanker and so on. I can change this to 30 and see what's going on. I have never tried.
No, so this is certainly very impressive, Rodney. So I'm looking a little bit also at the time, because I know that people are sensitive. So I know quite a few people are joining from the Netherlands, and this is usually around dinner time, and families are kicking in. I know in Spain it's maybe a little too early for dinner, but this is very impressive. Yeah.
And this is the last example. With this one, I have finished the presentation.